Okay.
Good, good. Okay.
Are we audible there? So, good morning, everyone.
Okay, let me talk. Can you all hear me? Can you still hear me? Good, good. Okay, okay. Let's start. You can take a seat. Apologize for the delay. Zoom had a sort of crisis this morning. It's either because my computer is managed by Cranfield and Howe, and there must be a firewall somewhere. It didn't allow to connect through York and everything. Anyway, we're here now. I'm starting. My name is Peter Zioupos, and I gave a title to this talk, A Bone-centric Approach in Biomedical Engineering, with the various applications in forensics, mechanobiology, and musculoskeletal research. So let's the next slide, if we come to the next slide. Okay, we're done. Okay, musculoskeletal research engages in a range of areas to do with performance, skeletal problems, genetics, disease, human factors, victim identification, because if you understand tissues well, you can identify victims in forensics, if you can imagine. Trauma analysis, that was my casework for courts, when people are stabbed or bones break or there's abuse, family issues and what have you. I think I have an example to show you. Identification, environmental effects, that's pollution and the effect it has on the human body. So basically that fits into three main domains, which is medical physics, forensics, and biomechanics, right? So the basic science is the science of bone and tissues, but of course it finds application and translation in all these fields, right? Okay, so, right, so some first visual sort of in one slide, a visual of all these structural function relationships and science of biological materials. So the three areas, as I said, is biomechanics, right? So characterization of tissues, mechanical characterization of tissues for disease and human healthy aging and diseased aging, identification of bodies for forensics, coming from the knowledge of tissues, and of course, biomedical engineering, which is use of ultrasounds, for instance, to identify the bone structures and use them in the automotive industry in this respect. So it's all in one slide, basically three different areas of application. Now, what's the basic science of this? Well, it's based on these three dualities: structure, function, cause, effect, and dose response. So structure, function, I started here 25 years ago in structural biology, trying to connect the structural effects and how they translate into function of tissues. So basically establish cause and effect relationships, because what is the cause that and how does it demonstrate on the tissue, and what is the effect it has? And eventually, in forensic biomechanics, when I found myself giving evidence in court, what the judge was asking was the dose effect a response. So basically, is the dose and the response related to each other? Because if it's unrelated, your cause and your effect could be unrelated as well. And your dose and response have to be related, otherwise the other dualities do not link, if you see what I mean. So there's a rationalistic basis in all this, and you have to establish a connection in these three dualities. Well, that maps well into where we do work. We work in the Department of Engineering quite often, in cross collaboration with materials and physics. And basically you have, again, three other areas. There's material science, that's the basics of what we do. Materials engineering, what we do with materials. And systems engineering, how we can fashion the various things together. Triple E, mechanical engineering, biomedical, all together. But the underlying science, the basic, again, is structural function, it's material science. This is the very basic. And all the others are sort of epi-science on the previous one. So that's the basics of it. So what did I do 25 years ago? 25 years ago, I was in the biology department here, working with John Curry in another block across the lake probably. And what I was working then was the very basics of bone damage. When bone fails, what are the underlying cause of it? And how does it demonstrate that? And how does damage exhibit itself? It shows itself up. And we produced these are 25-year-old pictures of microcracking damage in bone. So, and it's seen in various normal and pathophysiological conditions. So that's microcracking damage could be either of a diffuse nature, diffuse to the right here, because it's submicroscopical, subnanostructural, and of course it's diffuse. This is staining with fluorescent stains. And of course, at the more discrete higher level, nanostructural level, is discrete cracks of the kind that we see in aging human bone. So that was 25 years ago. And actually, I think these are 35-year-old, about a 60-year-old, the B, and a 90-year-old. And you can see that with age, these cracks accumulate in the human body. And that's what remodeling is trying to remove during the lifetime, ontogeny, during the lifetime of the individual. So that was the very first. That's my starting point when I first got involved in heart tissue research. So where did it go from that point? I went then in translation and translation of the knowledge and applications of this. So if we understand bone at the material level, what can we tell about normal disease and conditions? And I went into osteoporosis research, right? Actually, this is ultrasound modeled in a waveform, wave 2000, going through a human finger. So that's the ultrasound wave. We produce ultrasound prototypes to measure the properties of bone for the finger, the phalanx. And why does this translate into osteoporosis and weakening of the bone? Because that's what happens to the human body in 20 years in life. That's from the neck of the femur, actually. But that's from a 54-year-old cadaver, and this from a 74-year-old cadaver. So you can see that with the increase in osteoporosis, you lose a lot of bone mass. And of course, that reflects in the ultrasound signal. And then you translate the whatever quantitative effects of the signal into bone properties. So the ultrasound is a surrogate. And what the ultrasound gives you is a surrogate of the actual mechanical strength. Because at the end of the day, what you want to know is the mechanical strength of the bone. And how this translates into light or sound effects or anything is what you calibrate to tell what the mechanical strength of the bone is. So that's what we did for a number of years, actually, a couple of PhDs there. I will come back to this in a minute because that was used for automotive industry for putting ultrasounds in cars. Read the condition of the car occupants, the skeletal condition of the car occupants, and modify the restrainings of the car, which is the airbags and the seat belts, so as not to break the bones of the participants or the occupants if there's a car crash. So I'll come to that in a minute. I have a couple of more slides there. It's very interesting. So, right, what happens in bone though? What is the challenges when you look at bone science and how it translates? Well, is the heterogeneity of the material. So there's heterogeneity with age. So there's a 53-year-old female there, and that's a 79-year-old female. So it's like Swiss cheese, basically. If you look at bone, a cross-section from the femur with age, all you see is basically more and more pores with life. Also, the heterogeneity of the various elements. There's old and young tissue, older and young tissue age elements all gobbled up together. So obviously this increase in heterogeneity will demonstrate itself as increased brittleness with age. So here, for instance, we have some micro hardness values of the various elements in bone, and it has been published, of course, but you can have hardness of 44 up to 56, depending on what type of bone tissue you tap at any point. So really, what bone tissue is with age is a mosaic of tissue age elements, and the more heterogeneity and variability you've got, the more brittle will become, inevitably, right? So that was heterogeneity in situ and with age. Then we went into measuring bone material properties, if I can skip back, the challenge here you see is that, the challenge here you see is, and has been thought for a number of years, quantify the bone density or bone mass, and that will tell you 70 to 80% of the variability you see in bone strength. However, very few people looked in what this material is made of, this strand. So basically, the material is left later in life is of the same quality as the material in younger life. So there are material effects here that you don't grapple with. So the material bone changes here, not just how much of it you've got. And how does this change? Well, we looked first of all in the change of the apparent density with the material density of the bone. And here we have, that's the material density on this axis, and that's the apparent density. So what we've got here is low apparent density of bone, very osteoporotic. Here we have very solid or cortical bone. If you look in this spectrum, one, you can see that the material density of bone changes with the apparent density. It's not all the same. And it changes by quite a lot, actually, 1.5 to 1.9 something grams per centimeter cube. So basically, what this tells us is that when bone remodels, it doesn't remodel in the same rate everywhere. The remodeling rate depends on the active surface area, and inevitably, with osteoporosis, where the porosity level increases, what you've got is you end up with more dense and brittle material. So these struts that are left in osteoporosis at the end, the material has less bone mass and has higher local density or other strut density. So these effects always work in combination in life. Life, nothing is simple. It's not black and white. It's 1,000 shades of gray, basically. And it's all complementary or working together, just to confuse you. So that was something we did over a number of years, and we modeled that. We can do models of this now, take these relationships, if you can see my cursor here, take these relationships and remodel this. Start with a femur on a two-dimensional finite element model in the computer screen with the same density of material. And after millions of iterations, you can actually make it trabeculate and change its density to the density by putting the right loads on, simply reflecting to the loads to the local material density that you see in life. So really, that's a big conundrum, is it? Why is the femur shaped like that? Why is the internal organization of the femur the way it is? And well, yeah, is it genetically, is it life, or is nurture or nature? Well, it's both, but clearly loading has something to do with it. Because by putting the right relationships and the right algorithms, we can regenerate the trabecular pattern of a femur. We can recreate it. Okay, other studies. What I looked next, and that was very recent, actually, 2-3 years ago, was the age changes of bone in ontogeny. We said about heterogeneity with age, heterogeneity with in situ. Does the material bone itself changes with age now? Well, we know. Clinicians say yes. We reach maturity by the age of 30, 40, and then there's a downhill trend. So this is the whole skeletal structure of the person versus age. And these are these traits that you can see, right? For females and males. It's all hormonally sort of, there are some thresholds to do with hormonal function. However, what are these ages? Clinicians will tell you, and biologists, oh, thereabouts, 30 to 40, you reach maturity. You reach your skeletal height by 25. But, okay, is this precisely specified? Is it sort of a hand-waving argument? What is it? So what we did is, for the sake of it, I got tissue from 88 cadavers, from 17 to 88 years old, and we took sections from clavicles and ribs, and we did a number of studies on the bone material itself. Blind studies, regardless of age. Let's see what the tissue gives us. And this is the nanodentation tissue, the nanodentation data. And there was a precise point at 35 where something changed in the biology of the human being, right? So this one ethnic group, male and female, regardless, there was no difference between male and female. This is the bone material itself. So in other words, the females may have more porosity, but the bone material is the same, right? And you can see that 35, no matter how you looked at it, something changes in the physiology of the bone. So human bone material reaches maturity by 35, and then overnight something happens. Okay, I've been challenged by the referees when I published this in Bone. I've been challenged by every audience since then for the past 2-3 years, and they say to me, yeah, but how do you go to this threshold? Okay, how do you get to this threshold? And is it really so? Well, and I remind you something, each of these dots are lots of values from one individual. So we have here 7 cadavers at 36, we have 5 or 6 cadavers at 34. Something happens at this point. If you can see here, these are different individuals, they're all bunched up, right? There's no doubt that something happens overnight between 34 and 36, and the human biology changes. And if you look in other relationships, it's even more pronounced. So if you look here, for instance, this is the mineral content, the water content, and the organic content of the same bones. You can see the same effect. And if you look here, this is DSC, FTIR, XRT, the same. And if I'm lucky, I don't have the one. I have measurements of microporosity, intracortical porosity of these sections. And the people are bunched up right and left of 35 in 2 groups. So really something happens there. The human body is programmed to arrive at 35 and then change its sort of plan in life. I don't know, plan for retirement or I don't know what. Degradation, it doesn't matter. Anyway, so that's very interesting because the clinicians know that things happen then at that point. But what I'm looking at is the translated effects on bone material itself. And blind studies examine bone material, and that's what you get. That's interesting. Right. Okay, other things that I have been looking at and I'm interested in because it relates to clinical and point of care applications is diagnosis and prevention for osteoporosis with invasive and non-invasive measurements. So over the years we did that. We examined cohorts of thousands of elderly individuals and young ones with ultrasound, CT scans for modeling for automotive industries, car crashing sort of individuals involved in car crashes, or looking after their health in later life. So these are some applications. It's all helped by the underlying science that if you know what bone is and how bone behaves, then you can understand what these instruments tell you. So for instance, here we have the fracture toughness of beams of bone from God knows how many, I think it was about 36 individuals. And the T-score that came from ultrasound measurements from the wrists of these same people. So there are relationships. So really what you see in the ultrasound measurements reflects in the actual mechanical measurements. And these are fracture toughness measurements of the bone of these same people. So there is a relationship, and that demonstrates itself demographically in life, of course, isn't it? So these T-scores, for instance, do mean something in the material level, mechanical level. Now, other areas where this can help is in exercise science and things that happen to much younger individuals. So for instance, we know about stress fractures in soldiers, athletes, and dancers. I was funded by the Ministry of Defense to do a study on about 1,000 young recruits who are a very small age cohort, between 20 and 25. They experience stress fractures when they go through the basic army training. And these are young, healthy people. So basically, they are not in the category of brittle old bones or brittle old skeletons. They're healthy bones, but they're overdoing it. They're overloading their skeleton. And again, with a combination of ultrasound, CT scans, medical records, and questionnaires, you could actually find true positive and true negatives in predicting whether they're going to suffer a stress fracture. Okay, in this application, just for the sake of mentioning it, it was funded by the MOD because they're concerned, or they wanted to know, because they have a duty of care, if they enlist a certain individual in the armed forces, can they pre-scan them to know that they have strong enough skeleton to sustain the military training? Can they pre-tell or predict so as to spare them the pain later on? Because what happens is about 10% of the recruits do experience stress fracture, and that's the end of their career, because the only way to remedy the stress fracture is to send them home to recover. While they're sent home to recover, they will never re-enlist and rejoin the forces. So this screening at a very young age has the same pros and cons and the same great value than screening old ladies for stress fractures 50 years later. Anyway, so you can see it's two sides of the spectrum. Always material science links with technology to tell you something that you need to know, right? So that's the fourth application. Also funded by the Ministry of Defense was the spinal fractures that very strong individuals sustain because, again, of overloading it. So this was done in Portsmouth, that's the Royal Marines. They use these ribs, rigid inflatable boats. When these become airborne at the sea state 4 or 5, and then splashdown, all these 10 commandos, and these are strong guys, practically are taken out of action. Honestly, the forces are so much on the spine. Only the skipper there and another guy are sitting on anti-vibration seats of the likes that you can see in various things. All the others are sitting on a bench. The issue is so serious that these boats nowadays, especially in research environments, carry a black box. And after the mission, they're recording the vibrations they have experienced because there is a limit, there's a threshold. So this is studies we did on the vibrations and the effects of the spine. Again, it's linked to cancellous bone and the properties of cancellous bone and how it's loaded or overloaded. So, okay, it's basically a combination of human factors and safety factors in a human and musculoskeletal performance for individuals. Again, very strong and able men. And they are suffering damaging effects. Okay, that's another application. Spinal trauma, same thing. What a civilian would experience is fractures like this, compressed vertebrae. What these soldiers will experience quite often would be compressed vertebrae. It will be detrimental for their career, if anything else. Okay, right. Other very basic or very important research I've done over the years was in the effects of strain rate and age. Okay, come to think about it, most of the characterization of bone properties for the past 100 years was in quasi-static mode. Now, does any of us break bone in quasi-static mode? No. You won't break your bone if you carry your Sainsbury's bag full of goodies from Sainsbury's to home. That will be a static, quasi-static creep loading for about half an hour, right? Most of our fracture will happen at high strain rate and in later life. Right, okay, what do we know about these two factors? Very little, actually. So, but I've done some research in this, and they're very important to know how bone behaves in strain rates and with age. So, we'll display. I hope it will play. Right, there is some sound there, but let's do it again. So this is breaking. It goes half a femur, so it's a semicircle in a high strain rate in a quick sort of loading condition. What do you observe? The stored energy is so much that it has fragmented in many pieces, and the two left pieces are just flying away from each other, right? Just catapulted into the room, right? Now, believe it or not, that's what will happen in your femur when you sit in the car, you have a car crash, and your knees hit the dashboard. Only few cars carry airbags to protect the knees. But when your knees hit the dashboard, the femur gets into compression, experience up to 7,000 to 8,000 newtons, and believe it or not, it fractures to thousands of little fragments. It's a catastrophic failure in the middle of it because it bends under the compression. And that's the stored energy, phenomenal energy. Most of this fracture, okay, so let's see the next one. What will happen? I say, oh, is that true? Yes, it is true. That's the same kind of bone, more or less, wrapped in a cellophane, right, in a cling film. Same kind of energy. All the cling film does is holds the fragments together. So when you try to, when a surgeon tries to reconstruct one of these femurs after a car crash, he's got a hard work in his hand. All the muscles and the tissue did is hold together. This femur has fractured in thousands of fragments. There's a lot of energy going there at high strain rate effects. Okay, let's see another one. Right? Slightly lesser speed, slightly slower mode of fraction, you can observe a different effect. So what I'm saying is that the study of bone and the effects, the mechanical effects of bone, or what bone demonstrates, it's always contextual. And the context in this case is, what are the environmental conditions, the boundary conditions? What is the strain rate, right? So how do we examine this at the bone material level? Well, by actually producing samples from a femur, let's say, which are very small, much stick size. So let's do the same experiment and look how bone behaves, not as a whole bone, but as a small sample. Various strain rates. Let's see, that should play. So we have two matchsticks now here, 3-point bending. The first one is 64-year-old male, very fast. Right. That's how a piece of bone breaks at very high strain rate. And that's how it should break at a slower rate. Right. The fracture is not even complete. Right? It's much more controlled and plastic. It will certainly not brittle. Right. So what does this tell us? Well, there's many ways of looking at it. If we look at the energy that's been deposited, there's this 3D diagram. So we have three factors here. One is the strain rate, the other is the age, and the third one is the ductility of the samples. You get this surface. So really, the effects are three-dimensional. They're not two-dimensional, right? That's the first point to make. So if we go back now and demonstrate this a two-dimensional diagram, that's how it demonstrates itself. So if you put here, instead of putting mechanical measurement, strength, energy, or anything, let's use a stochastic variable. Let's use the percentage of the samples that broke in a brittle or a ductile fashion, and you get this. This is basically like the curves that you see in pharmaceutics and kinetics. This is 100% ductile to 0% ductile, or basically 100% brittle. And then you can see that this is the 85-year-old, 70, 55, 15. Now, 15 and below, we know clinically, that's where we experience the green stick fractures. Oh, there it is. Green stick fractures means nothing else other than increased plasticity for these bones. But the interesting thing is that when you do these stochastic curves, right, there's an order and a half magnitude difference between the very young and the very old person. So really, it's not simply how much energy the bone takes, it's not simply how strong the bone is at the time, but the whole is a combination of age and the strain rate. So basically, the young individual can experience 15 times more strain rate on the bones and still break in the same level of ductility like the 85-year-old. So, okay, whereabouts a 15-year-old can fall a number of times and don't experience a fracture, the aged person can fall 3 times and 1 in 3 will experience a fracture. And some anecdotal information, when I was speaking to Joe Carey 25 years ago, when we didn't have this data, he says to me, you know what he says? We're not designed to fall and break a bone ever so often. And we're not designed to do that very often. I said, what do you mean, John? He says, well, you see, as babies, we've been carried by the mothers, even as apes or monkeys, till about 2 or 3 years old, hanging to your mother. And then your bone becomes stiffer and carries you around nature. and is designed for us to climb an apple tree, grab the apple, and then jump back down to earth. We're not designed to fall from 20 meters height or drive a car and smash against the wall. And I said, yes, you're right. And the mechanical measurements tell us this nowadays. So really, we're designed for certain things, but not for others. And it's good to put some numbers to it, right? Good old John Curry. So what did we do next? The other thing that we can do, which involves technology and bone material properties, is produce the so-called, I call them triplets. You know about digital twins, where you have a physical model or a physical entity or some kind of tissue, and you produce a model out of it. So it's a digital twin. Digital twin is the twin of the physical thing. Well, nowadays, a physical member. So nowadays we can produce triplets. The triplet, the third of the equation, is a 3D printed something. So we did studies where we scanned skulls and modeled the skull in finite element and 3D printed them. So you have a physical model to play with. So that one, let's hope this plays, it's a plastic skull filled with ballistic resin or gelatin. I hope it plays. No, it doesn't actually. All right. Which has been, all right, okay. Let's see if that plays. No, it doesn't. Okay, I'll come back to it in a minute. So basically, it's been impacted at high strain rate to see how the skull behaves when it has a stress concentrating effect. Okay, basically, this hole here is a defect, which can be a result of, let's say, a tumor or surgical intervention. How would this skull behave? We need to know that. So that's what you combine here. You combine basically a mechanical setting where you have a 3D printed skull, a high strain rate loading. There's two skulls here, one with a defect and one without a defect, identical. And recording with high strain speed videos and producing the strain map in this same model. So basically you can model the skull, you can observe it breaking, and you can actually break lots of them because in 3D printing, we can produce thousands of copies of the one physical skull. And that's the benefit, right? There's only one skull. Even between identical twins, the two of them don't have the same skull or bone. If you scan it a 3D print, you can produce hundreds of copies of each one of them, right? Okay, so that's what the 3D printed model produces. So what does it involve? It involves scanning. It involves digital information. It involves manipulating of the image, 3D printing it, right? With and without a defect. You can change this in the computer. Filling it with permagel to simulate the brain and putting some strain gauges actually in the brain to calculate the strains or rather the accelerations, decelerations inside the brain cavity, then impacting it in a drop tower and looking at the effects. So that's the impactor. Everything has to be biofidelic, of course. And hopefully, and observe the results. The results can be of two forms. Can be quantitative, observing cracks emanating from the point of impact. This is not just for clinical study where someone has a brain surgery or some other surgery. It's also for forensic cases because most of the deaths involving criminality or other are from fractures of the skull for whatever reason, right? Let me see if that plays. Oh, be nice. Okay, there you can see it happening now. So there is a strain map image of the skull. The strains are on the right-hand scale. There's the impactor, has come down now and hit at the skull. You can see the strain building up around the circular hole, which is this little on that side of the hole. There's the impactor coming down. Here you can see the maximum strain building up still, right? The strain here is still building up. This is a very high speed camera, of course. Both the analysis and the recording and everything is done at thousands of frames per second. And at some point, I think, after it goes beyond the top load, you will see the crack developing here. Too small to observe. But you can see here how the three tally, the strain rates, the impact, and the observations. Right, okay. Interesting video. Is that another one? Yeah. It broke up there, and you can see some crack here and the concentration of strains around the crack. These are very invaluable, this kind of studies, for a number of things, both for forensics and clinical studies. Okay, sixth application. What's the next demonstration? Well, I have worked in a European project before, looking at the environmental effects on the skeleton. Now, we're talking about Ukraine, which apparently started the problem in 2014. We had an invasion in 2022. No, it started back in 2004, the problems there. That's a very good example. That was the president of Ukraine then in 2004. The first thing we knew in the West that something was wrong with him is when, I think is that the Telegraph or is the, I can't remember, when he was seen to sort of extremely unwell, and our press compared his image before and after a certain poisoning effect. He has been poisoned by dioxins probably. Most certainly. And that's the effect of these chemicals on the human body, right? I think he's still alive, and I can't remember his name. Was it Timoshenko and Poroshenko? I can't remember one or the other. So there was this president of Ukraine, has been poisoned then, and that highlighted what can happen if you get a huge dose of antibiotics in your body. Now, how do we get dioxins? So how do we get dioxins? Well, dioxins are produced or a byproduct of the degradation or the production of chlorinated PVC, polyvinyl chloride plastics. They're extremely stable. That's why they put chlorine in the plastics, because it makes it so stable that even nuclear bomb radiation and temperatures will not degrade this. So when they're out in the environment and they're released, they stay there forever, and they're very nasty. The other thing about dioxins, you get them from bleaching, of course, and various other processes. They're lipophilic, so fat absorbs them instantly, and they stay there to have their damaging effect. So where do we get them? We get them from petrochemical industries, released into the environment. They are picked up by lower down in the food chain, like fish. We eat the fish, and we reap the effects of them. So basically, it's pollution. The European Union has a directive now and tries to control all this. That's why PVC is phased out. They're quite drastic. These are cross sections of animal studies of a healthy rat and one that has been poisoned with dioxins. You can see the effects. So it's not good for you. Certain parts of the planet, for instance, it's all industrially produced, really. It's not a natural component. It comes from the petrochemical industry. Certain parts of the planet, like the Baltic, for instance, is completely polluted because of the sludge from all these industrial countries by dioxins. It has been said that the food intake, the threshold of food intake of fish from the Baltic, so you can reach the limit of damaging for dioxin, is only 2 or 3 cod a year. So don't eat Baltic fish, if that's true, right? Or fish from the Baltic. And that's because in a closed sea, there is no flow of water, and all the sludge that comes down the rivers from all these Scandinavian countries and around the Baltic deposit all these pollutants in this sea. So it's serious. It's around us. There's no doubt that plastic production, byproducts, and all the rest has a damaging effect. So that's what someone who is a biomedical engineer can do about by looking into cross sections and bone material properties before and after polluting effects. Okay, what else can we look at? We can characterize bone before and after pharmaceutical interventions. Like what? Use of bisphosphonates, for instance. If you don't know, bisphosphonates is what we use nowadays to combat osteoporosis. Bisphosphonates, in practice, kill osteoclastic cells. They don't promote osteoblastic cells, kill osteoclastics, the cells that break down bone. They are pollutants, actually. They have been discovered as a byproduct of other medicines when people realized that by being in the body, they're bad to the bad guys, the osteoclasts. So they start delivering them or administering them to combat osteoporosis. Right, okay. So what study did we do? A study we did a few years ago was to examine the bone of 3 groups of donors. The one that they had suffered, they had no fractures, osteoporotic fractures after the age of 70, let's say, from the Imperial College. This is a tissue bank in the Imperial College. Some that have suffered fractures and some that they have suffered fractures, but they had been treated with bisphosphonates. So if they're pharmaceuticals, if they're meant to help osteoporosis and have a good effect on this, what do they do to the bone tissue material? So there's the 3 groups: healthy people, untreated people who just suffered a fracture. That would be my mother-in-law. And people who suffered a fracture and had those bisphosphonates, that would be my mother. So, so basically all 3 groups in my family, right? What are the effects on the bone material level? Well, what's the best way of looking at it? And that will help me highlight another point in this lecture. The point is that the technology and what we make of bone, the 2 advance hand in hand. The more sophisticated and expensive the technology becomes, the more we can tell about bone. So here we use the 2 best kinds of material characterization technology that we know at the moment. The one on the left was to use the synchrotron diamond, X-ray diffraction, wide X-ray diffraction and small X-ray diffraction to characterize the microstrains in bone tissue under deformation in these 3 groups. And the one on the right is nanoindentation measurements of the bone matrix of these same groups. So basically, we characterize groups, bone mechanically with nanoindentation, and in the synchrotron under deformation, observe the strains, the nanostrains of the same bone tissue. What are the effects? Well, the 2 technologies gave us different effects. And that demonstrates probably one of the last points I want to make, is that if you look at nanoindentation, the 3 materials were classed as 1 to 3. You can see that it goes one way. And here we have controls, fracture treated and fracture untreated. In which case, basically, the fracture untreated showed itself as worse than the other 2 groups. If you go on the diamond, you get a different story. The fracture treated shows itself as worse than the fracture untreated or the control. So what does it tell you? Well, it's a conundrum, actually. It tells you that not only you have to characterize bone within its context, but also you have to have a more careful and profound look in what the techniques are telling you and what the techniques are translating for you, right? So looking at the same tissue level, 3 groups of tissue, you get different results depending on what technique you're using. And these are both mechanical techniques, right? So, and that's where the likes of me can discuss for years and argue in conferences about what's best to use. Well, it's horses for courses, or course for horses. Depends, use the technique that's more appropriate for the question that you have in hand. Right, okay. 8th application, forensics now, and forensic biomechanics. What are the challenges there? Well, what can you tell about the human body when it's been dismembered? What can you tell about the human body when it's been buried and found 5 or 10 or 20 years later? How much you can identify about the body by looking at the musculoskeletal remains. So this photograph, actually, that's from our group when I was working down in tsunami in Indonesia. And that's what you've got. Hundreds and thousands of bodies, they have to be identified. After a few days or weeks in the seawater, a lot of damage. DNA can be retrieved, but you need more sturdy or stable materials. So the skeleton is more stable. What can we tell from the skeleton? Can the skeleton tell us something about the individual? Well, that's a study we did some years ago. We had cross-sections from the femur from 7 males and 7 females across a group of ages. And we looked in the mechanical and biomaterial characterization to tell whether we can estimate the age of the individual. You see, when you have a missing person or an identifiable person, the 4 main characteristics that you want to know, I'll let you know, is age, sex, stature, and ethnicity. So if there is a missing person, actually the police puts out a call for a 35-year-old male of Caucasian who's about 5'8", right? So if you have these 4 basic characteristics, then you have somewhere to start with. So what about the first one, the age one? What can you tell about the age of a person? In the London bombings, for instance, the problem was not identifying the people. The problem is identifying the remains. As people are dismembered, you find pieces of bone all over the place. So where does this bone come from? What age was the person? So, and the problem then is, in analytical sort of terms, that age becomes indeterminate after the skeletal maturity or the height maturity of the person, because the curves flatten out. You see what I mean? So with age, the curves increase, and after maturity, they flatten out. So therefore, there's inaccuracy. If you're trying to tell age from any other analytical variable, a very small change in the variable will have a huge effect on age, estimated age. So that's where the challenge comes from. So what can we do about it? Well, we can do a number of things. What helps in this circumstance is that if you apply one technique, you have this inaccuracy in age estimation. If you apply 10 or 20, the errors cancel out, and then you can have predictions like that. We have here the age of the individual and the predicted age in a range of cadavers between 50 and 80. And by a series of methods, material and mechanical methods, we can produce algorithms that we can tell the age of the individual within 1 or 2 or 3 years. So basically, from skeletal remains, if you give me a fracture from the femur, I could place the age of this person between, let's say, 55 and 58, whereby if you ask a forensic anthropologist, pathologist to tell you that, he will tell you if he's an adult between 40 and 60. So laboratory methods can be made to be very much more specific. And we can do that because we know bone and tissues so much better nowadays than we used to. It's a benchtop and laboratory method as opposed to an experiential method. You see, when you watch silent witness, prime suspect, and all the rest, the forensic pathologist is an expert who does qualitative assessment based on his data bank and his brain and his past experience. He doesn't crunch numbers, right? Well, I can tell you it's better to crunch numbers because they will enumerate what you want to know. All right? So that's the last slide. What bodies tells us and what we can tell about human bodies and how knowing them better, it will improve all our lives. So thank you for listening. And I think, I hope I've thrown enough of technology in there to make it interesting for all of you.
Any questions from the audience online? Maybe on the chat.
Oh, therefore on the chat. Excellent. Here. Visible, audible. Thank you. Okay, no questions.
No questions.
No questions. Okay, I'll tell you, my email is simple, so I'm going to put it here. And you can email me if you think of questions later. That's one. And the next one is, well, I have same. Have their ACUK, that's it. So either of these emails, you can send me your questions over and we can have a nice discussion.
You have a question?
I just have one question. Talk about the viscoelasticity being important.
Yes.
Super important.
Yes.
Is there any effect from cadaver? Because if the cadaver he's dead,
Yeah.
I guess the material properties change,
Yes.
and therefore maybe they influence something like viscoelasticity.
Yeah. That's
Just
yeah. No.
what's
Yeah.
known and kind of is this a concern?
Within reason.
Okay.
Yeah. I mean, the studies I did is from cadaver, post mortem, from the deep freezer, so the bone was retained its mechanical characteristics as far as we know. I mean, most people when do these studies, they forget one thing, that the properties of bone that we measure, it's a snapshot of what this person was when he died, the day he died, at the moment he died.
Yep.
The day after or the week before, the musculoskeletal characteristics were different. So actually, if you think about it, you collect a biopsy or a bone material today, the day of the person died, and it's a snapshot of its condition at that particular date. And as you say, post-death, depending on the environmental conditions and how you retain it, that will change. So really, you have to confine this, control these characteristics. But yes, the week after this same sample will give you different properties.
Yeah, exactly.
Everything changes. It's a fluid thing, So, we take things as gospel and say, oh, these are the bone properties, No. Everything is contextual. Everything is, the boundary conditions matter. Everything depends,
Your experience, like, are there ways to mitigate that, or you just got to kind of accept it?
Laboratory conditions, right? Extreme care and everything, obviously, to maintain the most physiological life conditions. And then there's always an error, I suppose, isn't it? Even my measurements, any physical measurement comes with an error, isn't it?
Yeah.
So really, when I say modulus, I'll say plus or minus 5%. Anyway, so, I mean, when I try to measure, let's say, we try to measure with ultrasound, try to measure the bone strength of cadavers, because in bone and bone remodeling, the dexterity, if you're right-handed, left-handed, reflects on the skeleton. So, and if you're a professional, like a tennis player, Nadal or whatever, Nadal is left-handed, I think, and Federer right-handed, the serving side of the skeleton has 10 to 20% more bone mass and strength, right? So we reverse that in forensic biomechanics. Says, right, can we tell the dexterity of the dead person by looking at the bone condition of right and left wrist, for instance? Well, this change is about 5-10%. Well, the ultrasound instrument experimental error is 5-10%, right? It's comparable. So the biological variability is comparable to what experimental of any instrument anyway. So we did that. We did that in living and cadaver. And we couldn't tell the dexterity with any kind of thing because we're not all professionals, right? We don't train to the extent that we can have asymmetry. The most of us are right-handed or left-handed. And I think most murderers, victims are, but none of them is a professional tennis player, for instance. So, you know what I mean? There's so many questions to answer, and interesting stories to tell, But that's the thing. Always is within experimental error, biological variability. Can you measure? Same with aging. If the drop in the modulus of elasticity of bone is 10% per 10 years in life, we can measure. If it's 2%, as it is, it's a very shallow drop.
Yeah.
So your experimental error has to be much more specific to measure this drop, right? And then the biological variability, you have all the people right up and down this drop. So the variability between individuals can be 10%. And the drop between, let's say, 50 and 70 can be 10%. And your measure can measure within 20%, in which case you will never have a result. That's why using complementary methods and throwing everything together, ultrasound, mechanics, everything together, these noises, that's what I said, cancel out. Because for a certain individual, any individual, ultrasound will be +5, mechanical will be -5, physical chemical will be ±5. If you throw all the parameters together in the multi-regression, they cancel out. Right? And then you start, the more parameters you throw in, you can then start predicting. So the age estimation method, you can put mechanics together, physical chemical together, a lot of different modalities. And the errors cancel out, the noise rather, up and down, and then you specifically pinpoint the age of the individual, right?
Yeah, it's triangulation. Really.
Yes,
Yeah,
Yes.
AI is the
yes. Oh, yeah. Well, yeah, the question is, why does viscosity matter for bone mechanics, let's say? Well, collagen, I mean, one of the two main ingredients is collagen and mineral. Mineral is elastic, collagen is viscoelastic. So that's why when you test dry bone from wet bone, you get different mechanical measurements. The same way if you test, let's say, degraded bone in taphonomy, which is in the grave, or 10 years in the grave, is different from fresh bone. That's why also in viscoelasticity is the relatively content of mineral to soft tissue, right? The two elements, rule of mixtures and everything, right? So basically, one of moiety, the collagen is affected by all the environmental conditions. The crosslinks can be affected. It can sort of, the signature of the crosslinks can change, and that will change the viscoelastic conditions of the collagen itself. And then on the mineral phase, the mineral can leach out of the bone. So if you have a body buried in an acidic environment, it loses mineral a different way than you have a body in alkaline or a neutral soil, right? So that's why all this, the spanner in the works is all these conditions. But that demonstrates what we know, that the viscoelasticity of the bone material as it is in a fresh individual in life matters. And this viscoelasticity plays together with the ratio of mineral to collagen and the properties of the mineral and the collagen in life. So I have other experiments here, for instance, where fluoridization, you know that we have fluoride in our toothpaste for our teeth. That's good for the teeth because it protects against chemical degradation or attack, right? It's not good for the mechanical properties of the teeth. Fluoridization of the teeth reduces their strength by 10 to 20%. So mechanically has the deleterious effect. How does this work? Because the fluoride is absorbed immediately by the hydroxide groups, absorbed instantly when the fluoride is in the bloodstream or anywhere in contact with the bone. It incorporates into the mineral. So that all the fluoride does is it changes the mineral moiety of the bone. And the effect is strong enough to be demonstrated as the mechanical effect. So that's something that affects the mineral itself. So you either have more or less mineral, or you have different kinds of mineral. And then same with the collagen. You have more or less hydrated collagen, or you can have more or less cross-linked collagen. All this play, right? So you need to understand, you need to understand the context, isn't it?
yes, or the measurement.
Yes, but they forgot what the effect is.
Yes,
The effect is it's a chemical effect. It's against chemistry, right? Enzymes and sugars in the mouth. Acidic attack. It wasn't mechanical. So it's just, So fluoridization, yeah.
No, not that.
What? Yeah, in this context, the measurements of ultrasound is basically speed of sound.
Yes.
Speed of sound, because that relates to the density and the modulus of elasticity. So speed of sound, modulus of elasticity, density, the three link. So obviously you translate. Yeah. 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 So it's kind of either be reflected or transmitted. Various ultrasound techniques in the market do both. Some of them, so for instance, we use one of them was the Cuba Clinical. That's transmitting ultrasound through the calcaneus, So you have two. You have a receiver and a transmitter, emitter of ultrasound. But that some Instruments measure speed of sound. All you need to do is the distance, time of flight to get the speed of sound. But some other measurements, like the Cuba that we used here, was invented in Hull, actually, measure the spectral characteristics of the signal. So you have the spectral characteristics of the signal before and after, and you produce what they call it the broad ultrasound attenuation, the change in the frequency across the spectrum. And this change of frequency relates to the level of osteoporosis of the material. So these are two complementary variables. You can have the BUA and the speed of sound. Each one demonstrates or arises from some other physical cause effect. And the two of them together probably will give you a better prediction of the mechanical strength of the bone as opposed to having one or the other. Yeah. I'm not an ultrasound expert. I use ultrasound technology as I find it and see what it can tell me about bone, because I can characterize bone. So what does it tell me? How many green apples, red apples or green bananas? Right. Now, what does this mean in terms of mechanics? And then basically it surrogates a blind thing. So this speed of sound relates to these mechanical characteristics. It's good to know in clinical setting, know them. We use micro CT to download a skull bone and produce finite element models, as I did for the skull. So that was a CT skull, clinical CT. And you take this data to produce a finite element model and even produce a plastic model, a 3D printed one. That's how we use the CTs, the clinical CTs. Clinically is DEXA. DEXA is different. The DEXA produces a surrogate value. It produces a density, an areal density of bone. Density of bone per square centimeter as opposed to cubic centimeter. It's an areal density of bone. And that's what is used to place you in a spectrum with respect to your peers, right? So a normal distribution of your peers, Peter is here below, let's say the population average, so therefore he's osteoporotic because he's much weaker than his peers. If you're stronger, you're in the safe side. That's the clinical assessment by WHO. The clinical assessment by WHO is put a person in the spectrum with respect to his peers and for his age. And if he's 1 or 2 or 3 deviations below what's expected for his age, then he's in trouble. That's what osteoporosis assessment is now, really. You know.
This the reason I'm asking is there we don't know that most details.
Yes. Well, actually, because you mentioned density, the last papers I did the past 5, 6, 7 years was all about the density and looking at the density and what we mean by density. So there's material level density, there's apparent level density, right? And there's the density you see in the CT scan, the density you see by other modality. You know, different values, different things, you know, and most people, they don't make the distinction, really, you know. And when they write a paper or something, they don't tell the public what they mean by that. It's critical. As you say, the density is critical. Features in ultrasound, isn't it? You need to know the modules and the density and the speed and everything else, you know, absolutely. Yeah. Yeah, I mean, we can measure density in a number of ways precisely in the lab if we get a biopsy. But in clinical practice, right, okay, you know, when you have a living individual, you can measure density with various instruments. but take it with a sort of pinch of salt, because they have to be calibrated. I mean, clinical instruments are calibrated regularly in the hospital, but within their parameters, right? So DEX is calibrated with the phantom and everything every so often by the medical physics of the hospital. Every company has its own phantoms and standards, every instrument. So it's always, and that's why you look with regard to your peers. If I want to know what this person, the condition of this person is, I'm going to do the same measure across the population with the same instrument, same calibration, everything, and then I can place him with respect to his peers. In that case, they are all being treated the same way. And then we know that Peter is weaker than job log average, so therefore he's in trouble. Because it's all this physics underneath, isn't it? Physicists understand their own benchtop versus clinical and everything else. Yeah. So
I think there's no question online.
no questions. There will be some on the email.
Thank you so much, and it was wonderful pleasure having Professor Peter here. So once again, thank you.
So I leave.
Yeah.